In all of the previous sections in Chapter 4, we were focused on direct proof, starting with if P then Q, a conditional, and then supposing that P is true and showing that it compels Q must also be true. This is also our modus ponens, our universal modus ponens if we include our domain. So what we're going to do now is move into the types of indirect proof. The two types of indirect proof that we're going to be looking at are proof by contradiction and proof by contraposition. We're going to start with proof by contradiction. And that proof by contradiction, it's based on the fact that either the statement is true or false, but not both. Our method for proof by contradiction is to write out the negation and then try to prove that the negation is true. And when we do that, we will find that we reach a contradiction. And if we reach a contradiction, that means that our negation is false. And if you remember from all of our logic in Chapter 2, if the negation is false, that means the statement itself is true. This is why we call it an indirect method of proof. Because we are not directly proving that the statement is true, we're more directly proving that its negation is false. So we need a method for our proof by contradiction. So what we're going to do is, number one, we're going to suppose the statement to be proven is false. That is, we're going to suppose that the negation of the statement is true. Then we're going to show that this supposition logically leads to a contradiction, and then we will conclude that the statement to be proven is true. I often get asked, how do I know when to use proof by contradiction or contraposition instead of direct proof? My best suggestion is try to prove it directly, and if you can't, try one of your indirect method proofs. Sometimes you will be able to see a proof by contradiction before you can see a proof by contraposition, or vice versa. Sometimes you'll look at a statement and you'll go, I can't prove it the way it's written, but I know if I could just switch them around and make them the opposite, I could do it. And that's our proof by contraposition. So this section is essentially giving you a couple more tools in your proofwriting toolbox. So let's try one. In example 4.7.1, I said let's use proof by contradiction to show that there is no integer that is both even and odd. So much like before, we're going to start with our statement. And in our statement, we're going to say that for all n in the set of real numbers here, if n is an integer, then n is either even or odd, but not both. So this is essentially, we're proving the parity property here. That's what we're proving here. So this is the parity property that we used in section 4.5. So then n is either even or odd, and I'll put in parentheses, but not both, as a reminder. So our proof by contradiction says, number one, suppose this statement is false, meaning we're going to suppose that the negation of our given statement is true. In order to do that, we need to write out our negation. So let's write out our negation. And remember, the negation of a universal conditional is going to be an existential. There exists an n in the set of real numbers such that, remember, such that always goes with there exists. Such that, and remember that the negation of a conditional, so not if P then Q, is logically equivalent to P and not Q. So here we're going to say P gets to remain true, so such that n is an integer and not Q. So n is both even and odd. It is both even and odd. So we already know this is going to be a contradiction, but we'll see how we would write it as a proof. So our proof, I'm going to keep it in red because we are sticking with trying to prove that our negation is true. That's number 2. So then we're going to show that this supposition will logically lead us to a contradiction. Well, we can already tell our contradiction is going to be that a number cannot be both even and odd, but that's what we're trying to prove. So that's where things can get a little tricky. So here we're going to suppose, and the best part about using a proof by contradiction is that you get to suppose the entire statement is true, because it is no longer a conditional statement. So you can suppose n is an integer that is both even and odd. And that's exactly what we're going to do. Suppose n is an integer and n is both even and odd. So that's kind of an interesting supposition. Well, let's start with the definition of even, because we said that one first. So by the definition of even, we know then that n equals 2k for some integer k, for some k in the set of integers. Well, we also said here that n is odd. Well, so by the definition of odd, then we know that n is also equal to 2l plus 1. Or you can do 2j or 2p or 2q or something else. And I said for some l in the set of integers. So I'm hoping you can see where we're going next. We're going to say by substitution, don't we always? So by substitution, we know that n equals 2k and n equals 2l plus 1. So we know then that 2k equals, I'm going to say so, 2k equals 2l plus 1. And you're going, okay, I can already tell this is not going to be the same number, but we need to show that to our proofreader. So what we're going to do is we're going to subtract the 2l over. We're going to say 2k minus 2l now equals a positive 1. We'll factor out our 2, and we get k minus l, and it equals 1. So what ends up happening is we get k minus l equals 1/2. So we would say, thus, l minus k is an integer because integers are closed under subtraction. However, 1/2 is not an integer. So this is a contradiction. So we just hit step 2. Show that this supposition logically leads to a contradiction. And then step 3 is then to conclude that the statement to be proven must be true. So that's where we finish it out. We will say, now that we've gotten to a contradiction, we would say, therefore, there is no integer that is both even and odd. Even and odd. I will say, and then don't forget your QED or your box to show that our proof is over. I will say that a lot of these contradictions are showing that on one side you have an integer and on the other one you have a rational number that's not an integer. Or you have a number that's even and odd. Or something along those lines, you have a positive and a negative. Something along those lines are the kinds of contradictions you're going to be looking for. In this particular case, we found out that we had an integer equal to a non-integer. And that was our contradiction. So you can get a little bit creative in trying to figure out what the contradiction might be and finding a way to get there. As long as your logic is sound, you will be fine. So I feel like proof by contradiction is a bit more of a puzzle sometimes. Contraposition is still laid out very, very clearly, like all of the direct proofs are. So contradiction is the one where we get to kind of think about it a little bit more and see if we can solve a puzzle. So let's try another one on the next page. I will say this proof is actually one of my favorites because it's really fun, because now we're going to show that a number is both rational and irrational, which it's not allowed to be. We learned that in section 4.3. So we said here, use proof by contradiction to show that the sum of a rational number and an irrational number is irrational. So let's write our statement. Our statement says, for all m and n in the set of real numbers, if m is rational and n is irrational, then m plus n is irrational. Now we need to find our negation. So remember, our negation, our universal quantifier, becomes an existential. So there exists some m and n in the set of real numbers such that, because existential and such that go together. And remember, the negation of if p then q is logically equivalent to p and not q. So we get to keep between the if and then as is. So p stays the same. So such that m is rational and n is irrational. And now remember our then becomes an and. Now we get to negate that m plus n is irrational. So we will say m plus n is now rational. That's what we're going to try to prove. So let's see where we start. Let's suppose m and n, well, let's see here. M is a rational number. N is an irrational number. And m plus n is rational. So remember, because it's a negation, it's no longer an if-then conditional. We can suppose the entire thing is true because it's all a bunch of conjunctions. So we're going to suppose that m is rational, n is irrational, and m plus n is rational. While we don't have a direct definition for irrational, what we really do know about it is only that it's not rational. So that one's not going to help us. So we're going to lean into the definition of rational and use that for both m and m plus n. So by the definition of rational, we will say then m equals a over b. And now instead of n, because n is not a rational number, we leave n out of this equation. What we're going to say, m equals a over b, and m plus n, which we're supposing is rational, is now equal to c over d. For some a, b, c, and d that are all integers, and remember that we can't divide by 0, so b and d are also not equal to 0. Total throwback to section 4.3. So now, by substitution, let's see what happens. Before we get into the substitution, let's think what it might be. We have used that m is rational. We have used that m plus n is rational, but we have not used that n is an irrational number. So the trick to this one is showing that if we do m being rational and m plus n being rational, then we can do a substitution and show that n is rational, which would be our contradiction because we assumed n was irrational, and that will be our contradiction. So let's see if we can show that n is both rational and irrational. So by substitution, we know that m plus n equals c over d. And then we know that m plus n is now, well here, let's see here, and we know that m equals a over b. Now we can substitute that m into our equation. So we end up with a over b plus n equals c over d. So here we're going to solve for n. So subtract the a over b from both sides. So we have c over d minus a over b. And here is where things are a little easier than what we did in section 4.3, because you don't have to do the common denominator and show that you've got integer divided by integer here, because I never said you couldn't use closure of rationals here. And because we have addition, multiplication, or subtraction of rationals here, we know that n is going to be rational. So here we would say, thus n is rational because rationals are closed under subtraction. Could you go through the whole thing where you said that n is bc minus ad all over bd and use a zero product property and all that stuff? Yes, you could. I'm just showing you a way to get to it a little bit faster. So thus n is rational because rationals are closed under subtraction. However, n is also irrational. This is a contradiction. Therefore, the sum of any rational number and irrational number, is irrational. Let's scooch it up so I can write it in. Irrational. And it has been shown. So this was probably a much shorter proof than you thought it might be. Well, when reading the original, it'd be kind of hard to show that rational plus irrational is irrational. And in fact, in section 4.8, which we aren't covering in this class, we go through showing that the sum, say, of 2 plus the root of 3 is irrational using this property. So it's kind of a cool application. But that's another proof by contradiction. You'll get a chance to practice some more of these on the written homework and the online homework. Next, we're going to move into proof by contraposition. Proof by contraposition, while being an indirect form of proof, is going to feel a lot like all of the other proof writing we did in the rest of the chapter. The catch is here, instead of using our universal modus ponens, we're going to use our universal modus tollens. So if you remember, our modus ponens says if P then Q, P therefore Q. Our modus tollens, which relies on the fact that our universal conditional statement and its universal contrapositive are logically equivalent, says that if we have if P then Q, we can say not Q, therefore not P. So essentially what we're going to be doing here is we're going to take our conditional statement, we're going to write it as its contrapositive, and then we're going to use direct proof to show that its contrapositive is true. So it's kind of a neat way to write proofs. And I laid it out here in methods in this method with steps 1, 2, 3, and 4. 1, expressing our given statement as universal conditional. 2, rewriting it as a contrapositive. 3, proving that the contrapositive is true through direct proof. And then by logical equivalency, the original statement will be true. So much like in our proof with cases and our proof by contradiction, we have to have a conclusion in our proof by contraposition that shows that we understand the logical equivalency involved. Let's try an example. So in example 4.7.3, I said prove that for any integer n, if n squared is even, then n is even. If you try to prove this by direct methods, you would say, suppose n squared is even. Then you would say that n squared equals 2k. How does that show that n is even? Taking the square root? I'm not sure that would actually work. So we don't have enough information at our fingertips to be able to prove this statement directly, which is why we're using an indirect method. Could you use contraposition or contradiction? The answer is yes. They are very similar types of proof. In either case, we just can't use direct proof. So let's start with our statement, which says, for all n in the set of integers, if n squared is even, then n is even. And now we want to write our contraposition. So our contrapositive, so we'll label that contrapositive. And remember, with our contrapositive form, our quantifier stays the same. So it'd still be for all n in the set of integers. We still have an if then, but now we switch p and q and we negate them. So if n is not even, which is the same as odd, then n squared is not even, which is the same as being odd. See how that parity property makes this a lot simpler? So let's try proving this statement. So we're going to suppose n is an odd integer. Then we know that by the definition of odd, then n is equal to 2k plus 1 for some integer k, so for some k in the set of integers. And by substitution, what are we going to have? Well, we're only given n squared, so we would plug it into n squared. So n squared is going to be 2k plus 1 quantity squared, which is 4k squared plus 4k plus 1. And if we factor 2 out of the first two terms, we get 2k squared plus 2k, and plus 1. I will say this is often where I find students making a small mistake. I'll have students who will factor out a 4 here instead of a 2, and they'll go, but 4 is even. 4 is not the definition of even. The definition of even is 2 times an integer, not 4 times an integer. So make sure that whatever you're going to do here, if you're trying to prove now that n squared is also odd, you need to factor out only a 2 because we need it to be in the form of 2 times an integer plus 1. So let's get to that. We're going to let p equal 2k squared plus 2k. And then we know that p is an integer because integers are closed under, and hopefully you said addition and multiplication. So thus, if we continue our simplification, n squared equals 2p plus 1. Oh, let me erase my p and write it a little bit better. Yeah, let's write this better. There we go, 2p plus 1 for some p in the set of integers. So therefore, by the definition of odd, n squared is odd. And you might think this is where we end, but remember I said that we have to put in a conclusion that shows that we understand the logical equivalency involved here. So we're going to say it follows by logical equivalency, which you can abbreviate as LE. I'll write it out this time. By logical equivalency, that n squared is even when n is even. When n is even, there we go. And it has been shown. On the last page, we have one more proof by contraposition. So what I'd like to do is pause here, see if you can figure out how to prove example 4.7.4 with contraposition all on your own. Now that you've had a chance to try it, let's do it together. We want to prove that for every integer n, if n squared minus 6n plus 5 is even, then n is odd. So let's look at it. So our statement would be, for all n in the set of integers, if n squared minus 6n plus 5 is even, then n is odd. And now we need to write our contraposition. So our contrapositive is going to say, for all n in the set of integers, if, and now switch p and q and negate them both. N is not odd, which is even, then n squared minus 6n plus 5 is not even, which is odd. So now we want to prove that if n is even, then n squared minus 6n plus 5 is odd. So let's do that. So we're going to suppose n is an even integer. Then by the definition of even, we know that n equals 2k for some k that's in the set of integers. And then by substitution, we say that n squared minus 6n plus 5 is now equal to 2k quantity squared minus 6 times the quantity 2k and plus 5, or 4k squared minus 12k plus 5. And remember, we're trying to prove that this expression is odd, so we need to split the 5 up into 4 and 1. So 4k squared minus 12k plus 4 and plus 1, because we need that 1 left over. And again, when we factor out here, we are factoring out a 2, not a 4. I know you could factor out a 4, but it's not going to help you in this case. We need our form of n squared minus 6n plus 5 to be equal to 2k plus 1, or 2p plus 1, or 2 times any integer plus 1. So we have to factor out that 2. So we're left with 2k squared minus 6k plus 2, and on the outside we still have our plus 1. And now this is where we can let p equal the 2k squared minus 6k and plus 2. Then we know that p is an integer because integers are closed under, and let's see what all do we have here. We have addition, subtraction, and multiplication. So we'll put them all in under addition, subtraction, and multiplication. Thus, if we continue our simplification, we know then that n squared minus 6n plus 5 is now equal to 2p plus 1 for some p in the set of integers. This is the definition of odd. So we would say, therefore, by the definition of odd, we know then that n squared minus 6n plus 5 is odd, which is what we were trying to prove. But remember, we need to write a conclusion that where we say it follows, right? It follows by logical equivalency, which again, you can write LE because we use it so often. It follows by logical equivalency that n squared minus 6n plus 5 is even when n is odd. And it has been shown, and we have finished chapter